The morning air above Espiritu Santo felt thick, almost metallic, the way it sometimes did after an overnight rain that never reached the runway. The date was the early hours of May the 17th, 1943, and the sun was rising over the palm line in a thin, colorless sheet. Crewmen moved around the maintenance revetments of Fighter Squadron 11 with the slow, deliberate rhythm of men who had not slept enough for weeks. The only real sound came from the Pratt and Whitney R-2800, warming on the far end of the strip, coughing light blue exhaust as if it too were reluctant to start another day. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Captain Harold Dixon, United States Marine Corps, pulled himself into the cockpit of his 4U Corsair, the newest machine in the squadron, a bird he had flown fewer than a dozen times. At 30 years old, he was older than most fighter pilots, a former airline mechanic who had pushed his way into flight school only after Pearl Harbor. On that morning, he felt every one of those years. He tightened his harness, gloved hands stiff, and looked across the wing to the crew chief standing by the left wheel. The man gave a thumbs-up, an ordinary gesture, but Dixon felt uneasy. Something about the way the engine had surged during the warm-up troubled him. He advanced the throttle for the pre-takeoff run. The Corsair lurched, torque yanking the aircraft left. Even after months of training, that twist felt unnatural. He added right rudder, held it steady, but the engine sounded strangely eager, as if the propeller were biting more air than usual. It reminded him of the P-36 he had once flown during gunnery trials in Florida, its pitch stops miscalibrated, climbing too aggressively during takeoff roll. His radio crackled with the flight leader's voice. "Dixon, let her rip. We have weather over the slot today. We need every minute." He eased the throttle forward. The Corsair leapt ahead faster than he expected, tail rising in a controlled, purposeful line. The climb that followed, steep, clean, unnervingly strong, caught him off guard. He had never felt a Corsair surge upward with that kind of assertiveness. For a brief moment, the needle of his vertical speed indicator kissed figures he had never seen on the aircraft before, numbers bordering on the fantastical, the kind that pilots exchanged in mess hall rumors about tweaked governors or over-aggressive pitch settings. When he leveled off at 10,000 feet, breath calm and visor fogging lightly, he asked his wingman, "Did you see that? The climb?" "Yeah," the wingman answered. "New governor settings, supposedly. Heard a mechanic tweaked them overnight." Dixon knew enough about engines to doubt it. The Pratt and Whitney produced enormous power, but nothing came for free. Unapproved pitch changes risked overspeed, overheating, and catastrophic blade stress. Field crews were meticulous about such things, yet the aircraft had climbed like a machine relieved of hidden ballast. He said nothing more and remained on station that morning, escorting dauntless dive bombers toward a distant Japanese picket line. But as he returned to Espiritu Santo hours later, landing on a strip shimmering with heat, the question hung with him. What had changed? Something felt different in the propeller's behavior, as if the machine were revealing a capability engineers insisted it did not possess. That curiosity, born in the cockpit of a single Corsair on a humid morning in the South Pacific, would spread quietly through Marine squadrons during the middle months of 1943. Pilots began reporting brief, intense surges during takeoff or early climb, moments when the propeller seemed to bite the air with a predatory confidence. Nothing consistent, nothing repeatable, but potent enough to ignite whispers. Someone had altered the pitch stops. Someone had found a trick. Someone had been reckless enough to unlock performance the aircraft was never meant to deliver. The rumors drifted back to the maintenance tents, like the smell of hot oil at dusk. They were impossible to ignore. By the time Dixon submitted his post-flight report, the squadron's engineering officer had already heard 6 versions of the same story, and just as quickly, he dismissed them. Hamilton Standard had provided clear, non-negotiable guidance. Governor limits were factory set, pitch stops were calibrated to preserve engine life, and unauthorized changes were prohibited at the risk of grounding entire squadrons. The Corsair was designed to climb at roughly 3,000 feet per minute under optimal conditions, certainly impressive, but nowhere near the exaggerated figures creeping into pilot chatter. Yet those whispers were not born from imagination. They emerged from a more subtle truth, one woven into the complex fabric of the Pacific War. The Corsair, despite its massive propeller and brutal torque, possessed unrealized potential at certain power settings. When ambient conditions aligned cooler air, optimal humidity, a well-tuned supercharger stage, the aircraft could momentarily achieve brief spikes in climb performance. Those moments felt almost supernatural to the men who experienced them. But the deeper story, the one that would eventually rewrite how pilots understood the Corsair's engine-propeller marriage, began years earlier in quiet drafting rooms far from the Pacific. To explain why Dixon felt what he did that morning, and why pilots throughout 1943 sensed a hidden strength in the machine, we must return to the foundations that shaped their expectations. In the years before the war, American aviation doctrine rested heavily on a series of assumptions about power transmission, propeller efficiency, and engine longevity. Engineers believed that each new generation of radial engines would demand more sophisticated blade geometry and more precise governor control. The giant 13-foot and 4-inch Hamilton standard propeller on the Corsair represented the pinnacle of these beliefs, a tightly regulated system meant to control thrust, preserve engine health, and maintain predictable performance across the aircraft's entire flight envelope. The balance between pitch, RPM, torque, and manifold pressure was not a guideline, it was a sacred formula. Training reflected those beliefs. Pilots learned that the governor kept the propeller at an even speed, adjusting blade angle continuously to maintain RPM. They learned that modifying pitch stops was both unnecessary and dangerous. They learned, through manuals and instructors, that pushing the system beyond approved parameters risked overboosting the engine or exceeding RPM limits, damaging not only the aircraft but also the pilots. Differently, field maintenance records from the Solomon Islands, Fiji, and Espiritu Santo show consistent patterns. Air filters replaced at irregular intervals, minor governor recalibrations performed to compensate for humidity-driven RPM instability, low-pitch stops adjusted to reduce takeoff roll on badly maintained runways. None of these modifications were reckless in intent, they were survival measures, yet even small adjustments could change how the aircraft felt in the first moments of climb. A low-pitch stop, recalibrated by a fraction of a degree well within safe limits, could reduce propeller load just long enough for the aircraft to surge upward before the governor recovered. A governor cleaned and retensioned after too many hours in salt air might respond faster, creating a sharper transition between static takeoff thrust and dynamic climb thrust. Such effects were subtle, fleeting, and technically permissible. But to the pilots who felt them, they hinted at a hidden transformation. Dixon sensed it that morning because his aircraft had benefited from a rare combination of factors. Newly serviced governor springs, fresh engine oil, unusually cool dawn air, and a runway still damp from the previous night's rain. Nothing illegal, nothing reckless, nothing that violated the physics engineers insisted could not be bent. Yet to the pilots in the South Pacific, men whose lives depended on seconds of climb performance during chaotic takeoffs under fire, these variations felt real enough to defy theory. And when men encounter something that feels impossible yet undeniable, they create stories that try to explain it. Thus began the myth of the reckless engineer, the belief that somewhere, someone in the Pacific, had unlocked a forbidden angle, a dangerous secret capable of dragging the Corsair skyward at breathtaking speed. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. But myths do not grow without soil, and the soil had been prepared years earlier by the pre-war American faith in engineering precision, a belief so strong that when pilots experienced something outside the expected envelope, they sought human agency rather than environmental nuance. Someone must have changed something. Someone must have ignored a rule. Someone must have found a secret. As the rumors grew, the context around them became ever more important. The United States Navy and Marine Corps were still adapting to the Corsairs' quirks. Many instructors remained wary of the aircraft. Journal entries from squadron commanders in 1943 mention persistent concerns. Steep torque on takeoff, unstable carrier landings during early trials, and difficulties maintaining RPM consistency in humid climates. Pilots respected the machine's raw power, but few yet saw it as the refined instrument it would later become. That gap between potential and would not only reshape the aircraft's reputation, but also reveal how myths form in the desperate, fog-shrouded margins of combat. The truth behind the rumor would emerge gradually, not through dramatic confessions or hidden modifications, but through careful observation, measured reports, and a growing recognition that the Corsairs' propeller governor system behaved differently in tropical war than it ever had in controlled factory trials. And as this truth unfolded, it would expose the profound irony at the heart of the story. The myth of a reckless engineer had grown not because someone broke the rules, but because the environment of war had quietly rewritten them. What followed for pilots like Dixon was a slow unlearning, an erosion of unquestioned faith in engineering limits, and the beginning of a deeper understanding of how machines evolve under the weight of combat. But before that shift could occur, the men of the South Pacific needed to confront the full contradictions of what they were taught versus what they lived. To reach that moment, we must step deeper into the world of the Corsair, its design history, its governor mechanics, its propeller physics, and the wartime conditions that twisted them into something both familiar and strange. Only then can we understand how a simple cockpit sensation became the seed of a legend. The men who first assembled the 4U Corsair in Connecticut would never have imagined how their machine would behave after months of exposure to tropical heat, coarse, volcanic dust, salt-laden air, and maintenance schedules dictated not by engineering idealism, but by supply shortages and combat pressure. To them, the Corsair was an elegant integration of known principles. The great bent-wing fighter had been shaped by wind tunnel data, NACA research, metallurgical advances, and the steady evolution of constant-speed propeller theory developed during the decade before the war. The essential logic seemed unassailable. A Pratt and Whitney R-2800 double wasp was built to produce power. A Hamilton standard hydromatic propeller was built to convert that power into thrust, and a governor ensured harmony by adjusting blade angle to maintain a fixed RPM. In its cleanest form, it was a closed loop, orderly, predictable, loyal to the numbers printed in the pilot manuals. That certainty had been earned through long years of development. During the late 1930s, American test pilots and engineers had grown confident in the hydromatic system. They had refined the oil piston, polished the gears, improved the counterweights, and strengthened the blade shanks. Constant-speed propellers had turned from experimental curiosities into reliable workhorses that allowed pilots to extract stable performance from increasingly powerful engines. And because engineering culture in those years prized precision and rule-based systems, the men writing the manuals believed that variations should be minimal, controllable, and most importantly, foreseeable. By the time the first production Corsairs rolled out, this mindset was baked into everything: training syllabi, maintenance standards, flight test expectations, and the Navy's approval process. Instructors taught young pilots that the governor would ensure the blades never drifted into dangerous pitch ranges, that the propeller would automatically adjust to preserve the selected RPM, and that the overall system was tolerant enough to absorb unforeseen stresses without erratic behavior. This foundation gave the aircraft a noble but fragile aura of predictability. The pilots who took the Corsair into war believed in that predictability, even as the conditions in which they operated quietly undermined it. On the islands strung between the Solomons and the New Hebrides, the climate wore down machinery faster than manuals anticipated. Humidity crept into electrical connections, salt fog accumulated on governor housings, sand infiltrated, oil lines. At lower altitudes, the air was thick and hot, raising cylinder head temperatures and forcing pilots to manage cooling flaps, with an attention bordering on obsession. A governor that might have been tested for hundreds of hours in mild Connecticut springs was asked to survive the corrosive breath of the South Pacific for months on end. The men who maintained the aircraft were not amateurs. They were capable, disciplined, and methodical. But they had to make trade-offs. A governor showing sluggish response would be cleaned and inspected on a makeshift bench under a tent instead of in a factory shop. Calibration sometimes occurred with limited tools. Replacement parts, when available, might be of varying vintage, pulled from units that had been in storage since 1941. Under these constraints, a small deviation could creep into a system designed for strict tolerances, and that deviation might be harmless in itself, yet produce a cockpit sensation that felt shockingly different. Pilots like Dixon were attuned to those sensations. They trusted their machines, but they also felt every pulse of torque, every change in engine note, every slight shudder transmitted through the Corsairs' long nose and into the control column. So, when an aircraft leapt forward at takeoff with more vigor than expected, or when the initial climb felt just a few degrees steeper, the pilot sensed something unusual. By mid-year, similar accounts were emerging across several squadrons. Pilots spoke quietly, almost sheepishly, about short-lived surges in climb rate. They compared notes over mess hall tin trays, each man recounting a moment when the aircraft seemed to possess a ferocity greater than its published performance. No one claimed that the aircraft could sustain such climbs. They merely described fleeting bursts, sometimes only seconds before the behavior returned to normal. To an engineer reviewing laboratory data, such accounts might have seemed trivial. But to pilots who lived with the Corsair daily, the moments felt meaningful. And when men recognize a pattern too faint to document but too consistent to ignore, they begin to search for explanations. Some blamed humidity, others blamed fuel-grade variability. A few insisted the newer versions of the R-2800 simply ran hotter and meaner. But the most persistent explanation involved the propeller system. It was not that someone had deliberately altered the low-pitch stop or governor settings. Instead, pilots speculated that the governor's behavior under combat wear might be drifting at the edge of permissible tolerance. They imagined that a governor spring stretched slightly from heat cycles might respond differently when the throttle was advanced too quickly, or that a minor contamination in the oil pathways might delay blade rotation by a fraction of a second, or that vibrations during taxi might temporarily loosen internal friction. These ideas were not unreasonable. The hydromatic was a complex mechanism, sensitive to both mechanical precision and the viscosity of its working fluid. What the pilots sensed was not outside the realm of physics at all. Instead, it reflected the transitional moment when American aviation was moving from pre-war standardization to wartime improvisation. The systems that had been treated as elegant constants in peacetime were now being dragged into an environment that tested their resilience in ways no engineer could have fully anticipated. Yet the myths persisted. Men told stories of an angle unlocked in the Pacific, though no one could describe it precisely. They disguised their uncertainty by attributing the phenomenon to a nameless, reckless figure, someone who had supposedly ignored the rules and discovered hidden performance. But the truth was less dramatic. No man had broken the rules. The environment had merely stretched them. To understand why even seasoned pilots misinterpreted those moments, one must look more closely at the specific dynamics of the Corsair during takeoff and early climb. The massive diameter of the propeller, 13 feet and 4 inches, created enormous rotational inertia. The torque from the R-2800 could twist the aircraft like a hammer blow. During the first seconds of takeoff, before the governor had fully stabilized RPM, the system was in a transitional state where small variations in blade angle or governor responsiveness could produce noticeable differences in acceleration and lift. These transitional states were always brief. Once the aircraft reached a few dozen knots, airflow across the blades changed the aerodynamic loads, oil pressure stabilized, the governor closed its control loop. But those early moments, the ones when the tail was rising, the pilot was dancing on the rudder, and the aircraft was straining forward could feel dramatically different depending on subtle circumstances. When Dixon felt that surge on the morning of May the 17th, 1943, he had encountered a perfect storm of such circumstances. Air density was slightly higher than usual because of the cool dawn temperature. His aircraft's governor had been cleaned the previous day, improving its responsiveness. The runway surface was damp but firm, reducing drag, and his aircraft carried a lighter ordnance load than usual. These variables acted together to create a climb that felt momentarily extraordinary. But sensations, once shared, take on a life of their own. The pilot's stories reached the ears of squadron commanders. Some treated the rumors with dry humor, others grew concerned about unverified adjustments. Engineering officers filed cautious notes in their reports, aware that even rumors could lead to unauthorized tinkering if not addressed. Aviation evaluators traveling through the theater took informal statements, puzzled but intrigued. Slowly, a critical mass of attention formed around ITO, these fleeting cockpit sensations. The war had created circumstances that magnified small differences. A 10% gain in climb rate might mean life or death when rising away from a contested airstrip. And so the pilot community in the Pacific began paying closer attention to the Corsairs' early climb behavior, scrutinizing every tremor, every RPM fluctuation, every surge. As they did, they discovered something more profound than a hidden angle or a rogue adjustment. They found that the aircraft's behavior, rather than violating engineering principles, revealed how those principles became flexible under real-world stress. The pilots had been trained to think in linear terms. Specific RPM yields specific performance, specific pitch yields predictable thrust. But the realities of war introduced a spectrum instead of a line. This recognition did not come in a single epiphany. It emerged gradually, through comparisons, discussions, maintenance logs, and repeated sorties. By the time several Marine squadrons rotated back to the United States later that year, pilots were describing their Corsairs with a new kind of respect, more cautious, more nuanced, grounded not in manuals but in lived experience. The next stage of this evolution would not occur in the cockpit but in the maintenance tents, where the men responsible for keeping the aircraft alive began to uncover the deeper mechanical truths behind the pilots' stories. The maintenance tent at Espiritu Santo always smelled the same in the late afternoon. Hot oil, solvent, dust, and sweat mixed together into a kind of mechanical humidity that clung to every surface. The sound of tools tapping against metal drifted through the canvas walls, steady and rhythmic, like a pulse. For the men inside, this environment was a second home, and in its familiarity, they could sense things pilots could not: slight changes in oil color, the soft hiss of a governor bleeding pressure, the dull resistance of a blade cuff when its bolts were loosened for inspection. The men who worked on the Corsairs' propellers were not theoretical thinkers. They were practical artisans, some old airline hands, others fresh from crash courses in Navy technical schools. They knew that a constant speed propeller was a compromise between physics, hydraulics, and human hands, and they knew how narrow the line was between perfection and trouble. So when pilots began murmuring about strange early climb surges, the ground crews listened without judgment. One of the veteran crew chiefs, a man who had serviced propellers since the late 1930s, leaned over a hydromatic on a wooden stand and turned the blade by hand. He felt the consistent drag of the pitch-changing mechanism, the way a jeweler feels the balance of a watch movement. He had done this thousands of times, and in his fingertips he could sense if anything was wrong. On that afternoon, he found nothing unusual. The mechanism moved with the familiar, heavy precision of a Hamilton Standard in good condition. Yet, even as he found no faults, he understood the pilot's concerns. In the Solomon Islands and the New Hebrides, the difference between normal and almost normal could be invisible to the eye but evident in flight. Moisture might thicken the propeller oil. Salt crystals might accumulate inside the governor housing. Bearings might turn sluggish in the heat. Each factor alone seemed minor, but combined they could briefly alter how the pitch mechanism responded at low air speeds. As squadron maintenance logs accumulated through mid-1943, patterns emerged. Several governors required minor cleaning to correct sticky flyweights. A handful of low-pitch stop screws were found marginally out of tolerance, not dangerously so, but enough to warrant adjustment. There were also instances of oil viscosity shifting more dramatically than expected due to fluctuating storage temperatures. None of these issues produced sustained performance changes, but each had the potential to affect the propeller's behavior in the first seconds after throttle advance. This was particularly true on runway surfaces that were uneven or deeply rutted. During the initial roll, bumps transmitted vertical jolts through the airframe, and those jolts sometimes momentarily disrupted the fine equilibrium inside the governor housing. The flyweights might flutter for a fraction of a second. The pilot would hear a brief change in engine note, tiny, but noticeable before the system stabilized again. Such deviations were harmless, but to a pilot already sensitive to every vibration of the Corsair's long nose, they felt meaningful. The maintenance crews tried, as always, to bring the machines back to factory standards, but the factory existed only in memory. The conditions of war placed the aircraft in a perpetual state of gradual drift. No two Corsairs on the line were ever perfectly identical by the time they had flown a dozen combat sorties. Each carried small imprints of its operational life dust embedded in seams, worn bushings, oil that had passed through one too many high-temperature cycles. And because the Corsair produced such enormous power, those small differences could become noticeable. As the months passed, the maintenance officers began comparing the Corsair's behavior to what they had seen earlier in the war with the P-40 Warhawk and the SPD Dauntless. Those aircraft had also revealed quirks not fully captured in manuals. In the P-40, for example, variations in the Curtiss electric propeller's pitch change rates were common, especially in tropical climates. With the Dauntless, some squadrons reported momentary RPM fluctuations during steep dives due to minor governor lag. None of these quirks had threatened safety. They simply reflected the reality that test stand theories could not fully model operational conditions. The Corsair's hydromatic was more advanced than the propellers on those earlier designs, but it was not immune to the same environmental stresses. Its designers had imagined the system operating within a clean, controlled envelope. Instead, it was living in the chaos of frontline aviation, where engines were started dozens of times per week, where components were swapped under pressure, and where salt air ate at precision fittings with unforgiving patience. For the men maintaining the aircraft, the question was not whether the pilot's sensations were real, but whether they indicated anything dangerous. The evidence suggested they did not. The propellers that produced the brief surges behaved normally when tested. The governors, once cleaned, showed proper response curves. The engines ran at the correct manifold pressures and temperatures. Nothing pointed to imminent mechanical failure. But the more subtle question, the one that quietly bothered the maintenance officers themselves, was what these incidents revealed about the limits of the engineering assumptions behind the Corsair. The manuals treated performance as a fixed relationship between throttle position, RPM, and blade angle. Yet here was evidence that performance could shift slightly even when the mechanical system remained within permissible tolerances. It was an unsettling idea, because it implied that the boundary between acceptable variation and unexpected behavior was narrower than the manuals admitted. A maintenance warrant officer, reviewing several months' worth of field reports, noticed a recurring theme. The aircraft showed the most pronounced early climb surges immediately after receiving fresh oil, a recently cleaned governor, or a propeller that had been serviced for minor pitch stop adjustments. It was as if the system performed briefly at its most efficient closer to its ideal state than usual, before settling back into the normal range shaped by environmental wear. The recognition was subtle but important. Pilots were not feeling a rule being broken. They were feeling the machine operating closer to the theoretical limits that engineers had designed but rarely seen in the field. This realization spread quietly among the maintenance chiefs. They did not think of it in philosophical terms. They simply told pilots that the machines were healthy and that what they felt was normal for an aircraft whose systems were tuned up more than usual. But the idea stuck with them that the aircraft had two personalities: the everyday Corsair worn by the realities of island warfare, and the rare, sharp-edged Corsair glimpsed only in the brief window after perfect maintenance conditions. It was in that narrow space, the difference between good enough and as designed, that the seeds of the pilot's myth had grown. But the myth was not finished. As the next phase of the war unfolded and operations pushed farther north toward Bougainville and beyond, the pilots began to encounter new performance variations, this time not in the first seconds after takeoff but in certain climbs at mid-altitudes. And these new observations would challenge an even deeper assumption about the relationship between supercharger behavior, propeller pitch, and the limits of climb performance. By the final months of 1943, the tempo of operations had shifted. The early, desperate defensive flights had gradually given way to offensive patrols and longer-range escort missions as Allied forces gained control of more airfields. The Corsair squadrons now staged from Munda, Barakoma, and the newly improved strips edging toward Bougainville. These airfields, scraped from crushed coral and volcanic soil, were more solid and better maintained than the temporary strips farther south, and the aircraft performed differently because of it. It was during this period that pilots began noticing a more subtle kind of variation, one not tied to the initial takeoff surge, but to the middle part of the climb, somewhere between 4,000 and 8,000 feet, depending on temperature and power settings. These variations were not dramatic, nothing as sudden as the sensations Dixon had first felt months earlier. Instead, pilots described moments when the aircraft seemed to ease upward more willingly for 10 or 15 seconds, a brief lightness in the climb that then faded. These observations puzzled the pilots precisely because they occurred at altitudes where the aircraft's systems were supposed to behave predictably. In that middle band of the climb, the Corsair's constant speed propeller should have already settled into equilibrium, the governor maintaining RPM, while the pilot managed manifold pressure. The supercharger's first stage operated consistently at those heights. Everything about that segment of flight was supposed to be stable, but the Pacific rarely honored the expectations of engineers. The first clues came from a pattern that maintenance officers had not fully appreciated. Earlier, altitude affected not just power output but the interaction between the supercharger and the propeller system in ways that tropical conditions amplified. Moist, heated air rising from the ocean lowered density and altered the load on the blades. The R-2800's two-stage, two-speed supercharger compensated for this loss of density by compressing the intake charge, but its behavior was not linear. Depending on temperature and humidity, the compressor might deliver a slightly higher or lower effective boost than nominal. These small fluctuations could change the available torque by a few percentage points, enough to influence the governor's workload, even if the pilot's gauges showed nothing unusual. A governor under slightly increased torque might move the blades toward a finer pitch for a moment, letting the engine spin more freely before the feedback loop stabilized. The aircraft would not leap skyward, but the pilot might feel it grow slightly lighter on the stick, climbing a little easier before the system corrected itself. Such subtleties were invisible to the eye of a mechanic inspecting a propeller on the ground. They appeared only in flight, under load, at specific temperatures and pressures that no bench test could perfectly replicate. It was precisely this mismatch between clean laboratory assumptions and the messy realities of Pacific air that made the pilot's experiences so difficult to interpret. Marine pilots flying from Barakoma noticed it first. The strip sat near the shoreline, and afternoon flights often began with air saturated by evaporating surf. As they climbed into the drier layers above, the density shifted rapidly, disrupting the balance between torque, blade angle, and RPM for a few moments at a time. Some pilots reported that their Corsairs felt briefly eager in these transitions. Others said the aircraft climbed as if suddenly unburdened. None of them had words precise enough to explain it, but all recognized the sensation. As these reports filtered back, engineering officers tried to match them against known behavior. They consulted performance charts. They checked the supercharger ratios. They reviewed the propeller governor's adjustment tolerances. Everything on paper suggested that the variations were well within normal operating envelopes. But the pilots insisted that something about the mid-climb felt different from what they had trained for back in the States. Their insistence was not stubbornness. It reflected the way experienced aviators learn to trust tactile, acoustic, and kinesthetic cues as much as instruments. A pilot flying daily in harsh conditions develops a sixth sense for deviations too slight to register on gauges, but strong enough to be felt through the seat and controls. By late 1943, the senior pilots were comparing notes across squadrons. A few even kept informal journals detailing specific altitudes, times of day, and weather conditions, under which the Corsair seemed to display this brief climb sweet spot. Their notes showed remarkable consistency. Most placed the effect between 5,000 and 7,000 feet. Most described it as transient, and most associated it with unusually humid air near the surface, giving way to cooler, drier layers above. What fascinated the pilots was not that the aircraft behaved differently, machines always do, but that the differences came and went unpredictably. The Corsair was revealing a personality, a set of traits shaped by environmental factors that training had not fully prepared them for. Instructors back at stateside bases had taught them that constant speed propellers ironed out irregularities, stabilizing how torque translated into thrust. But the pilots now understood that constant speed did not mean constant behavior. The governor controlled RPM, not climb rate. Even with RPM held steady, changes in air density, temperature gradients, and transient torque loads could affect how efficiently the blades converted power into lift. This realization forced them to rethink the neat, linear formulas they once trusted. For some, this was liberating. It meant the aircraft had more character and more potential than they had been taught. For others, it was unsettling. If a propeller could behave differently without showing any fault, then a pilot could no longer assume that a normal-feeling climb always implied a healthy system. They had to learn to read the aircraft not as a static machine but as a living system with moods shaped by the environment. The maintenance crews also adapted. They began paying closer attention to the oil condition in the propeller dome, realizing that small changes in viscosity affected how quickly blade adjustments occurred. They tracked ambient temperatures and learned to anticipate which aircraft might display mid-climb quirks on certain days. They understood, in a way that manuals never taught, that the hydromatic system's response time was subtly tied to the temperature of the oil, the humidity of the air, and the age of the seals. And yet, even with this deeper understanding, the pilots continued to report the occasional surprising climb, the brief moment when the Corsair felt like it wanted to rise a little more eagerly than expected. These stories now carried less mystery but no less importance. They reinforced a dawning truth that both pilots and mechanics were beginning to accept. Wartime aircraft performance was not a single number, but a range shaped by the metabolism of the machine. The next development would push this insight even further. An unexpected discovery that emerged not from pilot sensation or maintenance logs, but from the systematic analysis conducted during squadron rotations back to the United States. There, in the calmer conditions of American test stations, engineers encountered data that challenged the pre-war assumptions behind the propeller governor system itself and confirmed what frontline pilots had sensed intuitively for months. When the first rotation of experienced Marine Corsair pilots returned to the United States in early 1944, their testimonies were quietly collected by engineering officers at Naval Air Station Patuxent River. This was standard procedure. Pilots returning from the South Pacific brought more than combat experience. They carried a mental archive of sensations and anomalies that no test environment could fully reproduce. Their debriefings became an informal bridge between the theoretical purity of peacetime engineering and the chaotic reality of war. Among the topics discussed roping maneuvers, supercharger temperature limits, the quirks of carrier qualification. One subject appeared so frequently that the evaluators set up a dedicated review table for it, reports of irregular but repeatable variations in climb behavior between 5,000 and 7,000 feet. The engineers did not dismiss these accounts. Many of the earliest Corsair test pilots had flown at Patuxent themselves and knew that wartime pilots developed a sensitivity to mechanical nuance far sharper than anything felt during factory trials. Their goal was not to prove the pilots wrong, but to understand the underlying mechanism. To investigate, the Navy requested a structured climb profile survey using freshly overhauled F4U-1A airframes. These flights were conducted over the colder, denser air of the Chesapeake region, very different from the saturated heat over the Solomons. The aim was simple: determine whether the aircraft's climb characteristics could show transient micro-variations even when flown in stable weather and maintained under ideal conditions. The first flights showed exactly what the engineering charts predicted: a smooth power curve, stable manifold pressure, and a consistent rate of climb slightly above 3,000 feet per minute at low altitude, decreasing as the air thinned. In short, a textbook performance profile. But the test pilots were not satisfied. They repeated the climbs with slight procedural changes, different throttle advance rates, different mixture settings, and most importantly, different propeller governor warm-up intervals. It was that last variable that produced the first unusual readings. The hydromatic governor relied on oil pressure not only for adjusting blade angle, but also for stabilizing its internal flyweights. When the oil was unusually cold, the system responded slightly slower to fine corrections. When it was very warm, the response became faster, but sometimes transiently overshot its target before settling back. This overshoot did not change the sustained climb performance, but it could alter the first few seconds of adjustment after a power setting shift or after entering a region of quickly changing air density. The data showed that a brief rise in RPM, sometimes no more than 50 to 70 revolutions per minute, could occur during these micro-adjustments. The increase was small enough that a pilot might not notice it on the tachometer, but large enough to momentarily change the thrust produced by the blades. When paired with the R-2800 sensitivity to temperature, this created brief windows of improved climb efficiency. Naval engineers began reconstructing the scenarios described by Pacific pilots: late afternoon humidity transitions, rapid vertical movement through temperature gradients, engines already heat-soaked from ground idling, and governors being asked to shift workload quickly after the supercharger's first stage boost increased. Under these conditions, a slightly warm governor, a dense top layer of evaporated moisture, and steady combat power could indeed cause a few seconds of what pilots called lightness or eagerness in the climb. It was subtle, but it was real. This revelation did not imply any dramatic leap in the Corsairs' capabilities. It did not rewrite the aircraft's official performance numbers or produce any new specifications. What it did was strengthen the credibility of the men who had described these sensations under fire. Their instincts had been correct. Machines did behave differently in combat environments where every component was pushed to the edge of its thermal and mechanical limits. This finding also carried broader implications. Before the war, American engineering culture prized precision and predictability. Flight behavior was expected to follow design curves with minimal deviation, but wartime operations had created environments in which systems interacted in ways that the charts could not capture. The hydromatic governor, the R-2800 supercharger, the local weather, the pilot's recent throttle movements, all influenced the machine dynamically. By the spring of 1944, the Patuxent engineers submitted a report summarizing these findings in precise, unemotional language. Buried within the technical language was a conclusion that validated what frontline pilots had learned through experience. Transient fluctuations in propeller efficiency and climb performance are inherent to constant speed systems operating in rapidly varying atmospheric conditions. For the pilots, the meaning was simpler. The Corsair had always been more complex and more alive than the textbooks suggested. This conclusion soon circulated through Navy and Marine aviation units. It did not change any manuals or operating procedures, but it shifted the tone of instruction. Instructors now emphasized not only the theoretical principles of constant speed propellers, but also the lived truth that systems reacted to the world around them. No two climbs were identical. Environmental cues mattered. Engine feel mattered. This shift in mindset proved invaluable as pilots transitioned into later Corsair variants with improved engines and different propeller patterns. The changes in equipment were meaningful, but the continuity and understanding was even more so. Pilots approached the aircraft with a deeper respect for its subtleties, and maintenance crews monitored factors once considered irrelevant to performance, like oil warm-up behavior and atmospheric transitions during the first stage of supercharging. In a war fought across half the planet, with thousands of airframes built by different factories and maintained under wildly different conditions, this recognition that machinery is shaped by circumstance became its own kind of wisdom. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.